Yes.
I told you to read the book, your textbook, Unit 22. Did you do?
So not the whole chapter.
Okay, okay. So you did how much?
First few pages.
First few pages, right? Okay, if possible, you read, huh? It will be better for you.
Yes, sir.
Look, so you write the heading action of DC motor. Action of
Yes, sir. Wait.
DC motor.
Action of DC motor.
Yes, yes.
Yes, sir.
Then you draw this diagram. You have here North Pole, South Pole, right? Of the magnet. Then
Yes.
you have one loop of wire. I see it's connected to the commutator. This is called commutator, right? And this is ring, right?
Yes.
Looking like ring, but this ring is splitted, right?
Yes.
So we say this one as split ring commutator. Okay.
Okay.
It's called commutator because it's making the connection commutate with the loop of wire and with the carbon brass along with the carbon brass it's connecting to the circuit, right?
Hmm.
That's why it's called commutator, and this commutator is split splitted, right? I
Yes, sir.
see that this side is connected and it can rotate, right? It can rotate, and when it is connected to this side, the other side is only connected to other side, not with this side, right? So
Yes. Yes.
this is the benefit of the splitting. We have only one side in contact once, right? Not two sides together in the
Yes, sir.
same side. It's the benefits of split-round commutator, and there with the consequences of this, we have some other benefits. We will go for discussion with them. Okay. Now we have this carbon brass connected to DC supply. Huh? It's battery.
Hmm.
And according to our need, we can increase or decrease the power supply. That means here we have rheostat. So by increasing the resistance, we can control, right? How much current we will pass through this motor. If we have more current, then the rotation of the coil will be more. If we have less current, the rotation will be less, right? As we learned before that by increasing amount of current, we can increase the turning effect, right?
Yes, sir.
In the coil. So uh, we are using this arrangement for doing that. Now, like before, we are having here rotation of the coil using the Fleming's left hand rule. Okay, Fleming's
Yes.
left hand rule we will use here. So you look here, we have here magnetic field, and we know that magnetic field direction is from north to south, isn't it?
Yes, sir.
Our first finger or forefinger or index finger, it is field, magnetic field.
Hmm.
Then the second finger or the middle finger is showing us direction of current. So
Hmm.
if you fix your finger according to that, these two fingers, first finger and the second finger, then you see part AB of the part AB, the direction of current is into the screen, right? Into the screen here. And the magnetic field direction, the first finger is right side. So what will be the direction of the force? Thumb.
So the isn't the middle finger pointing towards us? Like the first finger is from north to south, so it is
Yes,
pointing
yes,
right.
yes, yes.
So the middle
And the
finger should
middle
point
finger
to
is
us
towards the screen. Then thumb will be
upwards.
take again for AB, part AB, take. Part AB, it's into the page,
Oh, okay,
isn't it?
okay. Yes, yes. Then the force will be downwards.
Downwards. So it's now downwards force. So we will show the force here downwards, right?
Yes, sir.
So you level, huh? You level this one when you are drawing, and if it is downwards, then the rotation of this part will be upwards, isn't it?
Yes.
Then you see there is rotation of the coil is coming anti-clockwise. You see the arrow is given here, circular arrow. It's shown it is anti-clockwise rotation, isn't it?
Yes. Yes.
Now you complete the diagram. Then I'm writing some information. That one you write also, uh, just below the drawing.
So does every motor have a magnet? Can't it just turn using the current?
Yes, yes. Every motor we are using. I'm writing every motor has a current. Okay, current supply has a given current supply. Okay, has a given current supply. Okay, so you write this also. After drawing, you write this. Every motor has a given current supply, and we use current supply, then magnetic field, and we use Fleming's left hand rule to get the direction of turning effect of the coil. Okay, done. And the drawing, after drawing, you write this part. Then we are writing some more information about split string commutator. Huh? So here AB is going downwards, then CD is going upwards. When CD comes to the position of AB, then CD goes downwards, right?
Hmm.
Isn't it?
Yes, sir.
isn't it? And then AB goes upwards. So this way we have continuous rotation uh, of the coil because of the split ring commutator arrangement. Okay, so we are writing it
Yes, sir.
here. We write and drop it, and it will be more better. Split ring commutator, ring commutator helps the helps the coil to change the direction after every half turn, every half turn as the direction of current alters in part of coil every half turn. Carbon brushes, carbon brushes help the split ring to rotate to rotate smoothly with least friction, huh? Least friction, least friction. Carbon brushes help the split ring to rotate smoothly with least friction to get continuous with least friction to get continuous power supply. You got it?
Yes, sir.
So I think all the discussions about DC motor you understand, right?
Hmm.
So have you done with writing and drawing everything?
Yes, sir.
Hmm. Very good. So we are now taking the learning outcomes again. We have here look E and F, right?
Hmm. Yes, sir.
E and F for our learning outcomes for the DC motor, right? Can you see what is written here? Can you read again? E and F,
So which one?
E and F, E and F.
Discuss how this turning effect is used in the action of electric motor. Describe the action of a split ring commutator in a two-pole single coil motor and the effect of winding the coil onto a soft iron cylinder.
So we understand that how the split ring commutator is working, right? Now we have left the effect of winding the coil onto a soft iron cylinder. If you are winding the coil onto a soft iron cylinder, then we are having more stronger, right, forces, isn't it?
Yes,
So to make more stronger forces and rotation is much more stronger. That's why we are using soft iron cylinder. Is it clear?
yes, sir.
So we are done with this topic, huh? We are done with this topic. We will now take out the worksheet of this topic, right?
Yes,
Did I upload the worksheet before?
yes, sir.
Did you see it?
So I didn't try it yet.
Okay. Now you can see, right, on the screen. Hmm?
Yes, sir.
Okay. So what is the first question? Can you read?
A wire is placed in the magnetic field between the poles of a magnet as shown. When there is a current in the wire, it experiences a force. What change increases the size of the force?
Yeah, John.
So C.
Yes. Next.
Why is the coil of an electric motor wound on a soft iron cylinder? Uh, so B.
To
No,
strengthen,
no, D.
yeah,
D.
to strengthen the magnetic field. Hmm. I see. Ah, here is it. Okay. Easy, right? Now question 3.
A straight wire carries the current into the paper. The diagram shows three magnetic field lines around the wire. The current in the wire increases. What is the direction of the field lines and which change occurs to the field lines as the current increases?
So in your copy, are you writing the worksheet solution?
Yes, sir.
It is a worksheet of topic 22, question 1, 2, you got the answer, you write them, and 3 also. It needs some explanation. So where I am saying any explanation, write on your copy, okay?
Okay.
If it is possible, get the printout of this worksheet. Huh? That is
Yes, sir.
better because it will be your notes will be for the O-level exam. So what could be the possible answer?
Sir, not sure.
So it is right hand grip rule, right? Direction of field lines is clockwise or anti-clockwise. That one you can say.
It is clockwise.
Hmm. Now, if we know one thing that current increases, that means magnetic field also becomes stronger, right?
Yes. Then A.
Yes, the lines move closer together, right? We know that yeah, where the lines are more closer, their magnetic field is more stronger, right? From field lines property, we know that, right? Okay.
Yes, sir.
Are you writing the notes?
Yes, sir.
If field lines are closer, there is a stronger magnetic field. This is one point. Another point is if current is more, magnetic field strength is more. So it's clear to him. Then we go to 4, right? Hmm? 3 is done, right? Guilty?
Yes, sir.
So 4, read 4.
A current carrying wire lies between the poles of two magnets as shown. What is the direction of the force on the wire?
So use Fleming's left hand rule.
Yes, sir. Sir, B. Out of the plane of the paper.
Very good. Very good. So 5, you continue 5.
A coil P of N turns is made from a length L of wire. The coil carries the current I when between two magnetic poles. A similar coil Q of 2 Newton turns is made from a two length 2L of identical wire. It also carries the current I when between the two magnetic poles. Which coil has the greatest resistance and which coil experiences the greater turning effect?
Yes, think of.
So the Q should have the greater resistance, right?
Which one?
The Q would have greater resistance, coil Q.
Mm-hmm.
Then so it is D,
Dhaka.
C or D. I'm not sure.
Greater turning effect. To get greater turning effect, what we need?
More current.
Mm-hmm. So which one has more current?
Both of them have the same current flowing, except that Q have two end turns.
So,
Then
so, so what should be our answer?
then D.
Dhaka.
Yes.
No confusion, right?
No, sir.
Correct. Then 6.
Sir, 6 is D.
You got it already, right?
We did it already.
Yeah. 7.
7. The diagram shows a silver DC motor. What is the part level Q? B. Oh no, D. A slip ring. Oh no, it's commutator. Sorry, sir.
Yeah, it's a commutator. It is split ring, not slip ring. Huh?
Yes, sir. The diagram shows a current carrying wire in a horizontal magnetic field. Which row shows the direction of force experienced by the wire? Sir, B.
Yes,
Bangladesh.
yes.
The diagram shows the DC motor with its coil horizontal. What? Why is a split ring commutator used? Sir, B.
Which one? Bangladesh.
Yes.
Yeah, correct. Then continue.
Two long parallel conductors carrying current lie in horizontal plane. The two conductors attract one another. The two currents must.
Attract, right?
Yes. In the same direction. A.
Hmm. Yes.
A student moves a magnet into a coil of wire as shown in the diagram. The coil of wire is connected to a sensitive emitter, which chain does not produce an increase in reading. Um, so D on a CC.
Speed of the magnet. Actually, this one you will understand more in the next topic. It's directly involved with the next topic. It should be what is said. Which one is said? See,
Yes, sir.
uh, actually, by increasing the speed, we are having induced current, right? By
Uh,
moving the magnet. So, if we have more speed, we have more induced current. That one next topic
yes.
we'll understand. But here,
Okay, sir.
resistance increasing the ammeter, that is having no function here. Okay,
Okay, sir.
so we have here the answer is Bangladesh. Huh?
Okay.
Structured questions. Great.
Figure 1.1 shows a coil of wire connected by flexible leads to a switch and a battery. The coil is placed between the poles of a permanent magnet and is free to turn about the axis. When the switch is closed, forces due to the current act on the sides of the coil. The coil starts to turn. On figure 1.1, draw arrows to show the direction of the forces.
Hmm. So what should be the direction? So we have a magnetic field, right?
Yes,
We can consider that magnetic field is right side. Then we have here current direction, right? Positive to negative, eh?
yes.
So it's going like this. Hmm? Isn't it? Have you got it?
Say, it says the direction of forces. It's the
Yeah,
magnetic.
current direction you got, magnetic field you got, then now you can get the force, right?
Yes.
So what will be direction of force? If you think of any of the part of the coin,
Like
like
upwards.
uh, this one, this one is upwards, right?
Yes.
So we give here upwards. Uh, and this one will be downwards, right?
Yes, sir.
So here we label also, label we here forces, force, right? Also label here force. Okay,
Yes, sir.
done.
Yes, sir.
And now next,
B. B. The coil stops when it is vertical. Explain why the turning effect of the forces is zero at this point.
at this position, why? Why there is no turning effect?
As it is perpendicular to the force.
Hmm. So there is no horizontal distance between force, between the forces, right? We have uh, two forces, right? No horizontal distance between forces. Why we are getting actually turning effect? The turning effect we are getting as the current flowing through the conductor, that one has one magnetic force, right? Isn't it?
Yes.
And already we have another magnetic force. So when they overlaps, that time we are having turning effect, right? Now,
Yes, sir.
when we have these two forces in a direction, that there is no horizontal distance between these two forces. then we have no turning effect, right? They don't overlap, right? Hello.
Yes.
So that's why we are not having any turning effect. That means here the magnetic force created and the magnetic force already have, they don't have any horizontal distance between them. What is the condition for moment, right? You know, moment is the name of turning effect, right? Another name of turning effect.
Yes, sir.
So we don't have any perpendicular distance. That's why we have no moment, no turning effect that time. Is it clear?
Yes, sir.
Okay, then next, continue the next. Please go to the next part. Read this part.
In order for the coil to rotate continuously, a split ring commutator is connected between the battery and the coil. Explain how the split ring commutator enables the coil to rotate continuously. Include a diagram in your answer. Split
Yeah.
ring commutator helps the coil to change the direction every half turn as the direction of current alters in part of coil every half turn.
So again, say what you said. Again, say please.
In order for the coil to rotate continuously, a split ring commutator is connected between the battery and the coil. Explain how the split ring commutator enables the coil to rotate continuously. Include a diagram in your answer.
So they are saying include a diagram. That means you have to draw the diagram. Okay. The
Yes, sir.
diagram just now you got about the motor. That one with leveling you have to draw.
Yes,
You have to show brushes. You have to show split ring uh, connected to the brush, then connected to the battery. For that one only you have 2 marks. Then you see that each side of split ring touches uh, other terminal of brush and current reverses in the coil, changes terminals to connection to battery, right? So every half turn it changes the direction, isn't it? So every half turn it's returning or changing the reversing the sides, right? Coil
yes,
to get the rotation continuous, right? In the same
yes,
direction. So you write this, huh? Write and draw both. You are having 4 marks.
so I'll write this one that split ring commutator helps the coil to change the direction every half turn as the
Hmm.
direction of current alters in part of the coil
Yes, yes. For
every
writing only this part, you have 2 marks, and the drawing part, you have
yes.
2 marks. Do it, please.
So in the MCQ, I think they showed a simplified diagram of this. Can I draw that one?
Which one, please?
I think in the MCQ there was a simple diagram of the splitting commutator and the motor.
Yeah, 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 yeah. In MCQ part, right?
Yes, sir.
Yeah, you can use that one, but there should be labeling, huh? This one, huh?
Yes, sir.
Okay, sorry. Are you done with drawing?
Yes, sir.
Yeah. Then you are writing, right? Hmm. It's part you are writing.
An electric circuit consists of a battery, a variable resistor, and a connecting wire. Sections P, Q, and the QR of the connecting wire are in the region of space where there is a uniform magnetic field. Figure 2.1 In Figure 2.1, shaded area represents the shaded area represents the magnetic field.
Hmm.
The direction of the magnetic field is into the page. A
Hmm.
current can wire in a magnetic field can experience the force. In the table, mark one tick in each column to indicate the force on PQ and the force on QR.
Okay, so we have to know here the direction, right? Direction of current here, right?
Yes,
It's going in this direction here, and here it's going in this direction, right? Now using the Fleming's left hand rule, you check how this wire is moving. That this wire will be the force working. The Q part and QR part both, because only these two parts in the magnetic field, right? So magnetic field into the page, that means your first finger will be towards the screen. Second finger for PQ, it is right side. Then your thumb is upwards, right?
yes,
And for this part, for QR, you change the direction of your magnetic field in the same direction, change the current direction, then you see the force or the thumb is right side, isn't it?
yes, sir.
So we are getting the answer from here. For PQ, section PQ, a force towards the top of the page. For section QR, a force towards the right of the page, right? So we'll give tick here and here, right?
Yes,
Is
sir.
clear? So on your copy, write
Yes,
force for 2A, a force, so for section PQ, a force towards the top of the page, and section QR, a force towards the right of the page. Done?
yes, sir.
Yeah, read. Part B, read.
The battery in the circuit in Figure 2.1 is reverse state and explain the effect of this on PQ and QR.
Yeah. state and explain the effect of this on PQ and QR. Just reverse, right?
Yes, sir.
The circuit in battery, whatever the current direction is reverse. Then what will happen? Opposite, right? PQ and QR.
Yes. Yes, sir.
One will be downwards, another will be left side, right?
Yes.
So write it. So what will be the effect of decreasing the current?
Weaker magnetic fields.
Yeah, so force force will be decreases, right?
Yes.
Yeah, we actually have the magnetic field already, right? So now
Yes.
we are having the current. For this current, we are having the force, right?
Yes.
So that is turning effect or turning force. So we are having that force less if we have less current. Is it clear?
Yes, sir.
So we are done with this worksheet. Yeah? So we will start our next meeting at 6:45. Huh?
Okay, sir.
Okay, after 7 minutes. Come back after 7 minutes.